Hello networking enthusiasts. No matter if you are a sysadmin, DevOps engineer or a developer, you should know your firewall. Today I will introduce you to Nftables, a successor to widely used IP tables. We'll learn how to build a simple stateful firewall to protect your server. I will show you a few basic concepts like counters, sets, and concatenations. My name is Philip, let's get started. Here's what's the task at hand. We have a server with 172.27.97.1 IP and we want to allow traffic from two clients' machines. One that ends with .2 address and one that ends with .3 address. Traffic should be allowed to the SSH service listening on port 22 and also to the application service listening on port 8080. We want to block all other incoming traffic. That's a pretty common scenario. To simulate the application, I've updated the SSH service to also listen on port 8080. The service is now listening on both ports. To test the connectivity, you could use the telnet command, but a much better approach is to use netcat. -w option allows you to specify a timeout. If a port is blocked, it will abort the connection after a specified time. As we are on the local network, the maximum time I want to wait is 1 second. -v provides verbose output and -z tells netcat that we want to test the connection without sending any data. Port 22 on the server is open. Port 8080 is also open. Let's go to our server and start drafting our firewall configuration. You interact with Nftables using the nft command. There are a few ways to do it. You can just type nft and specify a command to run. For example, if you'd like to list existing firewall rules, you can issue nft list rule set. As we have no rules, the output is empty. We can also enter interactive mode with nft-i. It allows you to run commands like this. We won't be using any of those methods. The best way to set up the Nftables firewall is by loading rules from a configuration file. This has certain benefits, one being atomic operation. This means that Nftables will load everything into memory and swap the configuration. If you script the configuration in IP tables for a few fractions of a second while the script runs, your configuration is not complete. I will start by creating our configuration file. At the beginning, we'd like to remove all rules with flash ruleset command. Then we need to create a table. Table is like a namespace that groups all your rules together. You start with table keyword. Every table has a family that covers the traffic type it will process. IP is for IPv4 packets, IP6 is for IPv6, inet is for both IPv4 and IPv6, and there are few more family types. We'll go with IP for IPv4 traffic. Then we need to provide the name. I will call the table filter as we'll be filtering out the traffic, but you can name it whatever you like. Then we need to create a chain that will group our rules together inside the table. In IP tables, we had few predefined chains, but in Nftables you can create your own chains as you please. Let me name the chain input as it will be processing incoming traffic. In order for a chain to process traffic, you need to either jump to it from another chain or attach it to a netfilter hook. A hook is a place in the kernel netfilter framework where other modules can register callback functions and basically intercept and perform actions on a packet. At the end of the video, I will list basic hooks. As we'll filter incoming traffic addressed to our server, we'll attach to the input hook. In other words, every packet addressed to the local processes will be evaluated by rules in our chain. In order to attach our chain to the hook, we provide the chain type as filter, the hook as input, and set the priority as filter. We'll talk about different chain types and chain priorities in another video. Apart from attaching our filter chain to the input hook, we need to define a default chain policy. It tells the firewall what to do after the last rule in the chain is evaluated. We can set it to accept, so the packet will keep traversing the networking stack, or we can set it to drop to discard the packet. There are also a few others that we won't cover today. We'll set it to accept. Let's create our first rule. I'd like TCP traffic coming to destination port 22 to be accepted. That's it. One important thing to mention is that rules are evaluated sequentially, top to bottom. So if you have a drop rule on the first position and accept rule on second position, traffic will never be accepted as the drop rule will be discarded. Something to keep in mind. Finally, let's load the configuration with nft-f and provide the configuration file name. I will look at the configuration with the nft list ruleset command. Okay, all looks good. Every new packet addressed to the server will go through our input chain. If the traffic is addressed to port 22 TCP, it will be accepted. If the traffic does not match any rule, it will also be accepted due to default policy. Not that useful, but is a start. How do we know that this configuration even works? The easiest way to check that is to add a counter. What it will do is count the number of packets and bytes since the last counter reset. Let's reload the configuration and check how it looks. Do you see that? Traffic to port 22 is already counted by our rule. Important thing to mention is that the rule is evaluated left to right. In our case, the rule first checks if the traffic type is TCP, then if it's going to port 22, and only then counts the traffic and accepts it. If we put counter at the beginning of the line, like this, and reload our configuration, we would discover that this rule is counting every packet no matter if it's UDP. So please be careful where you place your counter statement. It should be placed just before the accept or drop keyword. For our rule to start blocking traffic, I will put drop at the end. This will cause any traffic not accepted by previous rules to be dropped. I will prepend it with the counter keyword so we know how much traffic got discarded. Because we have a rule that accepts the traffic on port 2020, we should still be able to connect. Another important thing to note is that by putting the drop keyword at the end of our input chain, we not only block inbound traffic coming from the outside of the server, but also traffic originating from within the server via the loopback interface. This loopback traffic should not be blocked as many services rely on that to operate. Let's add another rule at the top. I will start with an IIF keyword that will match the input interface index. We'll talk about interface matching in a separate video as there are few ways to do it and each method has its pros and cons. Then I will put allow as the interface I want to match and finally counter to count that traffic and accept to allow it. Okay, this rule will allow incoming traffic to loopback interface. Let me load and show the configuration. I didn't get disconnected, so that's a plus. Let me try testing the connection to our server from client 1. The connection works. At first sight, everything looks good, however there is one issue. If I try connecting from the server to the external world, I get a timeout. Why is that? If we dump the traffic on our external interface, we can see the reply packets, but our process is not getting the traffic. The thing is, our firewall is blocking the reply packets. How to fix that? Luckily, it's possible to allow incoming traffic if it's a reply to a traffic initiated by the server. For that to happen, we'll utilize the connection tracking mechanism inside the kernel that tracks the state of network connections passing through the system. We'll discuss contract in a different video. Let's list the state of the contract table with contract-l command. We can see established connections. Information from the contract table can be used to make decisions on how to handle incoming and outgoing traffic. That's called a stateful packet inspection, as we are tracking and making decisions based on connection state. Let's start by adding a new rule. CT state indicate that we'll be matching connection state from the connection tracking table. Established means that we want to match packets from a connection that's already established. Related means that we want to match packets from a connection that is related to an already established connection. Counter means we want to count such packets and finally accept them. This should be sufficient for our outgoing traffic to start working. You may ask, the reply packet from a TCP three-way handshake does not make the connection established. So why is it allowed? If a contract sees a SYN packet, it considers a connection as new. If it sees a SYN ACK reply, it considers a connection as established. Let me load the configuration and try pinging Google DNS one more time. We can see that reply packets are allowed as they are part of an already established connection. Of course, for ICMP protocol, we cannot say that the connection is established, as this status is only for TCP, but contracts can match ICMP request when ICMP reply. If we utilize connection tracking, then the next thing we can do is to drop any invalid packets. By invalid, we mean packets that are not associated with any known or expected connection or protocol. Those can be malformed or corrupted packets that can be potentially malicious and harmful. One last thing that we can use our connection tracking for is to allow only the first SYN packet that creates a new connection. Let me show you what I mean. We want to accept only the first packet that starts the connection to our SSH port. We match contract state new for TCP port 22. Only a SYN packet that starts a TCP connection will match that rule. All subsequent packets won't be passing through that rule, but will match the rule that handles established connections. Let me load the setup. Then test the connection from client 1 and list our configuration. Do you see that the rule matched only a single packet? The SYN packet for that connection? All other subsequent packets that make the connection went through the rule that matches established connection state. Let's check where we are at. We have a basic stateful firewall that allows traffic to port 22 TCP from any host. It also allows return traffic for connections initiated from the server and allows traffic to the loopback interface. Our firewall blocks all other incoming traffic. I will go to client 1 and try connecting to our application port, that's 8080 TCP. As expected, it does not work. Let's try opening port 8080 TCP where our application is listening. First thing that comes to mind is to add another rule. We want to match a connection in a new state with protocol set to TCP, destination port set to 8080. Let's count it and allow that traffic. Now I will reload the configuration and test the connection one more time. It works. If we look at the counters, we can see a single packet matched the 8080 rule. Let's start optimizing our simple firewall a bit. First, I'd like to have a single counter that sums incoming traffic on port 22 and port 8080. So far we've been using anonymous counters, but Nftables allows you to create a named counter. To do that, we should start with counter keyword and then provide the name of the counter. Let's say cnt_SSH. Then let's update our rules with the counter name. Mind that we did provide the same counter name for both rules. Finally, let's reload the configuration. I will now try connecting from the client to port 22 and port 8080. If we list the firewall configuration, we can see that the counter values disappeared from our two rules, and instead we have a single name counter that sums the traffic to both ports. Next optimization that we'll introduce is to consolidate our two rules that match traffic for port 22 and 8080 into a single rule. Nftables allows you to use sets. Let me show you. I will remove the 8080 rule, and in the first rule I will put the 2020 port inside the curly braces to indicate the value inside it will make a set. Then I can add a comma and provide an 8080 port. Basically, the rule will match TCP destination port for any of the values listed in the set. It is very convenient as it allows you to consolidate your rules. Let's check if that works. I will load the configuration, then go to the client and try connecting to both ports. Works. Our goal was to allow the traffic to certain ports from certain IP addresses. At the moment, only specified ports are allowed, but one can connect from any IP. Let's try to limit the IP addresses that are allowed to connect. To do that, I will update the rule with IP as other, as we want to match the source IP, and then let's provide IP of client 1. If we analyze this rule one more time, from left to right, we look for a new connection with source IP 172.27.96.2 and destination port 22 or 8080. We count it by cnt_SSH counter and then accept it. Let's load the configuration and try connecting from client 1. It works. Let's try connecting from client 2. As expected, the connection from client 2 does not work. We did only allow a single IP. Let's quickly fix that. We are already familiar with anonymous sets. Let's use one to group our client's IPs. I will put curly braces around the first IP, then put a comma and provide the second IP. This rule will match new connections from those two source IPs to those two TCP destination ports. Such setup is okay if you have a few IPs or ports to whitelist. However, there is a better way to do it. We can create a named set and reference it in the rule. Let me show you how to do that. First, I will create a new set with the set keyword and name it allowed IPs. You need to specify the type of elements that your container will store. The easiest way to do that is by typing the type of keyword and then providing the type. In our case, we want the elements of the set to be of type IP source address. Finally, let's add some IPs with elements equals, and then we list all the elements separated by comma. Then we go to our rule and replace the anonymous set with add and then name set. Did you see what just happened? We did extract the list of source addresses from the rule into a separate set. Now, every time we want to add or remove a new source IP, we can update the set without changing the rule. Basically, we did decouple the rule from the list of IPs. This will also allow us to reuse the sets in various places. I load the configuration. See how it looks. Let me try to add a new IP to the set from the command line with nft add element and then provide the table type, table name, set name, and finally the IP. If we list the rules, we can see a new element has been added to the set. Last thing I'd like to show you today is called concatenation. It's easiest to show you how it works by following the example below. We want our rule to match source IP and destination port, right? We can extract those two things, that's source IP and destination port, into the set. We can write it down like this. Source IP followed by dot followed by TCP destination port. In other words, the set will provide those two items. Let's go back to the definition of our set. We need to modify the type, as we'll be storing not only the source IP but also destination TCP port. Our elements will be different. Each element will consist of the source IP and then the dot and the destination port. I will put all four combinations. Let's load the configuration and list the rules. See what we did? All IPs and ports are decoupled from the rule. One last final check and we are done. I did promise you to look into various netfilter hooks. Here it is. First, the packet arrives on the ingress hook. The ingress hook is attached to a particular network interface. Here you could perform filtering at a very early stage. Then the packet traverses the pre-routing hook. When a packet enters this hook, it's intercepted just before the kernel performs any routing decisions. At this stage, the packet has arrived on a network interface but has not yet been processed with respect to system's routing table. Most common action that is performed on that hook is destination IP address translation. For example, we can update the IP of the packet address to our server so that it will go to a different server. Then we enter the routing decision phase. The kernel analyzes the destination IP address of the incoming packet and matches it to the entries in the routing table. Based on the most specific match or the most suitable route, the kernel makes a decision to route the packet for local delivery, assuming the address is associated with a local system, or forward the packet to appropriate network interface or gateway if the destination address is on a different network. Assuming its local address, the packet will traverse the input hook. That's the hook we'll be using today. Its main purpose is to decide the fate of incoming packets destined to our local processes. Should those be allowed or dropped? Assuming we allow the traffic, it will reach our local application. Then we move to outgoing traffic originating from our local process. First, it hits the routing decision and then goes to the output hook. At this stage, we can filter any locally generated outgoing traffic. Then we move to post-routing hook. At this point, the kernel has made necessary routing decisions. Most common operation at this stage is source address translation, where we replace the source IP of the packet with the IP of the outgoing interface so that return traffic knows how to get back. Then the packet goes to the network interface. If the destination IP is on a different network, the routing decision will point the packet towards forward hook. This hook is for packets that are neither locally generated nor specifically destined for the local system itself. The primary purpose of forward hook is to handle packets that are being forwarded by system from one network to another. Here we can perform filtering of packets in scenarios where a system is functioning as a router or gateway. The traffic goes to the post-routing hook and out to the network interface. Today we've just briefly learned what Nftables can do, so you can build a minimalistic firewall. Stay tuned, as next time we'll learn how to automatically add items to sets. We'll optimize our simple firewall even more with the use of verdict maps, and also we'll learn how to debug our firewall and log the traffic. In the future videos we'll also talk about forwarded traffic, packet manipulation, load balancing and offloading.